Hello and welcome to this quick introduction to Opera simulation software for the design of synchronous reluctance machines. Opera has been in commercial development since 1984. In 2018, Opera joined Dassault Systemes as part of the Simulia brand. In this presentation, we'll look at how Opera is applied to the design of synchronous reluctance or SynchRel machines. Here's some sample geometry of a typical SynchRel, showing a cross-section of the laminations. The stator is very similar to a brushless permanent magnet motor. It's typically a multi-phase stator, usually three-phase, and it could be a single or double layer winding. We then have essentially a salient pole rotor. The way that the saliency is provided is by the introduction of non-magnetic barriers. They could be left as simply air gaps, but more usually they'll be pockets of epoxy for structural integrity reasons. These barriers make it easy for the flux to flow parallel to the barrier through the steel, but it's difficult for the flux to cross the barrier. You can see there are no windings on the rotor, and there are no permanent magnets used at all in its construction. In this case, it isn't a permanent magnet assisted SynchRel. So it's purely due to the reluctance torque that the machine turns, and as the name implies, the rotor is synchronized with the traveling field provided by the stator windings. This type of machine is not new, thus far having been used primarily for industrial processes running at mains frequency and synchronous speed. In this slide, we'll take a look at why the design of a SynchRel machine is a multiphysics challenge. Magnetic flux flows freely parallel to the barriers in the rotor, and hence there's a low reluctance LD. Flux on the quadrature axis is impeded by the barriers, and hence there's a high reluctance LQ. Torques increase by improving the LD-LQ ratio. Hence we want to increase the width of the magnetic barriers, but this affects the mechanical integrity of the rotor. To improve structural strength, bridges can be introduced into the barriers. This has the effect of locally strengthening the component without overly affecting the magnetic circuit. An example of this is shown at the bottom of the slide, where two designs, each consisting of a single bridge of varying width, have been investigated. The wider supporting bridge reduces the peak stress from 300 to 220 kPa, as you might imagine, but this does also reduce the torque from 27.6 Newton meters to 25.7 Newton meters. So you can see there's a trade-off in the geometrical design between mechanical integrity and operating torque. Obviously this happens because you're affecting the LD-LQ ratio. As you increase the thickness of the bridges to improve mechanical stiffness, reduce the reluctance on the quadrature axis. It's very quick and easy in Opera to say carry out an electromagnetic analysis, pass forces to a structural analysis, then reperform the electromagnetics analysis using the deform shape in Opera 3D. There is, in essence, no limit to the complexity of the sequence, and we have implemented this for all of our physics solutions. In some designs, this will be more important than others, but with this tool set, at least investigating the level of influence is relatively simple. Here we can see an exaggerated deform shape superimposed on the SynchRel. The actual deformations are of the order of 20 microns, so not so large, even against a small actual air gap of a couple of millimeters. But you can see this is not a uniform reduction of the air gap, so a simple sensitivity analysis sweep scaling the rotor diameter wouldn't give the same insight as this true deformed shape. This deformation leads to a change in electromagnetic performance, which again is relatively easy to perform. If we look at the radial component of the air gap flux density around the machine and superimpose the results of the deformed shape on top of the undeformed shape, there's barely any noticeable difference at first sight. But if we zoom in on part of the graph, we can see the change in performance due to this deformation under load. This is a successful prototype design, so the difference isn't significant versus the desired performance. But this wasn't the case for all of the possible designs considered in the design space. Opera has for some time contained a module called the Machines Environment, which uses a wizard-style data entry for ease of use. The environments are written in the Opera programming language that's fully documented and are available to users, so they're not merely a closed executable. Common types of machines are offered, but in the developer version, the command files are mainly open source, so the user is free to make adjustments to the standard command file. This could be a small tweak to a slot shape, right through to a completely new topology of rotor or winding. Relevant data in terms of standard machine parameters is gathered for the machine being analysed. Then the environment builds a full fidelity finite element model. Analyses are submitted automatically to the batch processor. Then standard post-processing commands automatically generate plots and reports such as torque speed curves. This environment's been extended under this program for SynchRels. Here we see two typical dialogues presented to the user to start the machine definition. Some basic definitions start the process with the state of properties being entered first. Then, moving on to the rotor, multiple choice menus allow the user to select from circular or trapezoidal voids and the number of barriers. Obviously, the shape of the void then governs the subsequent geometrical data input. More data is required of the user for a trapezoidal void than a circular one, for example. Following this, the geometric model and the mesh are created automatically. The mesh size calculated automatically, but the user has the chance to override the default setting to either perform a quick coarse analysis or to define a fine high-resolution mesh for final detailed checking. For the dialogues, prompt for the required material properties and also the properties of the drive. For example, the user can specify the windings, operating voltage and current, and the frequency and speed. Users have the chance to override default drive circuits with circuits of their own. If loss calculations are required, the user enters properties required for copper and iron losses. Here we see a list of analyses to choose from in the machine's environment for a SynchRel, or any other type of machine for that matter. They range from simple electromagnetic analyses looking at static torque versus angle, through to dynamic and inductance analyses. Here we see the static torque analysis results, showing graphs of radial flux density versus angle, and also the torque versus angle for different operating currents. Moving on to the multiphysics analyses, here we have the results of the coupled run. This is converged after a series of electromagnetics and stress analyses, and we're showing the converged deflections due to electromagnetic forces and static displacements. Anyone currently performing three-dimensional machines analysis is probably wondering at this point how they can fit such wide-ranging but computationally expensive analyses within their development timescales. Two-dimensional analysis is normally used up front to perform some conceptual design before embarking on the more accurate and rigorous three-dimensional work. There is in the machine's environment basically a switch for the user to say whether they want a two-dimensional run or a three-dimensional run, and no data is lost. No extra is required. We've also worked on implementing parallelization of the solution process to make the most of the multi-core processors being installed in standard laptop or desktop computers, as well as high-end servers. Here we see the effect of switching between two-dimensional analyses and three-dimensional. The 3D model, as shown previously, took 41 minutes to solve over 1 million elements. Cut that to a 2D slice and you're left with 7,000 elements. The conductor lengths are adjusted automatically by the software so as not to introduce spurious end effects, and appropriate boundary conditions are automatically added to the model. The solution then takes a mere 2 minutes, even though we're solving a full 360 degrees. So a 20-fold increase in throughput. But we haven't lost any of the data from the 3D model, so reflation of the model back to 3D is a simple task. If we look at the results for air gap flux density at the center of the machine, we can superimpose the results for the 2D slice on the results for the 3D model. You'll see there's very little difference because the lossy flux at the ends is relatively small for this particular device. So if you were designing for an air gap flux density, the 2D slice results would most likely be adequate for first pass design. But of course, what we're not doing with 2D slice is capturing the end effects. The fact that we can simply switch between 2D and 3D analyses at the model build stage means that we can accurately but easily investigate the end effects when we're ready to do so. Thank you for joining us for this very quick overview. Please don't hesitate to contact us for more information or check the Dassault Systemes website for further details.